Okay. So, as promised, today we'll be looking at We'll be starting to look at shooting mechanisms. So, we already looked at a few types of lift mechanisms, like the basic like bars, like 2 bars, 4 bars, reverse double 4 bars. Although that's not enough to do justice for all the types of lifts that there are. Like for example, we haven't touched on cascade lifts or like scissor lifts, for example, that you can see in the real world sometimes, especially scissor lifts. Like those are more complicated, and we'll probably save those for later once we go through more of the more common and simple concepts. So yeah. So we're looking at shooting mechanisms, just like more variety now. So we looked at how to lift things, how things drive around, now shooting. So an example of like a year where you needed to build a shooting mechanism to like basically succeed was Turning Point. Basically, just like a really quick description of Turning Point. Basically, you have flags which you can see on my screen right now, and you have to like shoot at them, like shoot balls at them to toggle them to your alliance's color. So you have to shoot objects at that. You can't just make your robot like extend really high up and like just touch them all. That's illegal. You have to shoot them. So yeah, today we're gonna look at catapults, like using a catapult to shoot things, and a team that used this was 21S, and I'm gonna show you guys right now. So basically with a catapult, they can like basically load 2 balls and shoot them both at once, which is why this team probably chose catapult over like a different type of shooting mechanisms like flywheels, like we discussed a bit in the chat, or like punchers, for example. So yeah. Um, Another good example would be Team 365X. This team also like very similar design catapult as well. And unfortunately, I don't really have any photo libraries of any like good catapult teams, so I can't share any like this time. So yeah, but there's a lot of good reveals online about catapults, and 365X and 21S are some really good examples. So that's basically how it works. That's a different mechanism. That's a 2 bar you see there that the robot just used to flip things, and that was just a catapult. So yeah, and this is a 2 bar. So that's basically the preamble, and now I'll present the inventor stuff. Okay, I hope you guys can see, and yep. So this drive face was from way back when in lesson 2, like our gear 257 RPM drive face. So we'll be using this, and notice how we always like to use tank drives to like, or like personally me, like I like to use tank drives to base like catting, because like tank drives are just much friendlier to work with as they have much more mounting points. So that's like why a lot of teams gravitate towards tank drives, but nonetheless we'll get started. So the first thing we need to build a catapult is like a tower, right? Like a tower on which we can mount the catapult on. So start by just modeling that.
Okay, so I built a catapult back in grade 2 years ago for Turning Point. Mine obviously wasn't, because that was my first year. It obviously wasn't as clean as the ones that you see in the reveal. But I could just speak to like some of the first thing that you want to be considering when you're building a catapult. I think the first one is the most important thing that you need to be looking at is like how much power you want to be looking at how much power you want in your catapult as one of the first considerations. So the way that the catapult generates power, unlike some of the other designs, like for example flywheel, instead of like using like continuous speed to generate power, catapult generates power based on the amount of torque you generate in your motors. So you bring down the catapult arm is elastic up very strongly, and then you use your motor. Your motor is set to like a very high torque setting. So like in V5 that would be like the 100 RPM cartridges, and then you would gear it like 1 to 5 or something like that. And then you bring down the catapult arm, so you're putting energy into the system by doing work against the elastic bands. Then we're going to talk about the slip gear later, but once the slip gear releases, what happens is that all of the accumulated power generated, like that you've accumulated by bringing down the catapult arm is released at 1 second or in 1 instant when you release the catapult, and then the arm flings up. So one of the best advantages about the catapult is that it has like one of like the different shooting methods. Catapult, I would say, has like the highest like straight power output that you can get from one of the from any shooting mechanism. For two reasons. One, because instead of like flywheel, which is like you're not really storing any energy, you're just like you're using the energy to spin the shooter or the wheel, for example. But it's not being like accumulated. Whereas the catapult, because you're like you're spending like energy to first like bring down the catapult arm and then store it in the elastic bands. And it's all of that energy that you're storing up for all that time is released in like 1 instant. You're able to generate like a ridiculous amount of power from the catapult. Like I've dented like several times my wall just by like missing a shot. Don't do that. Another thing about the catapult. Oh, sorry. The cost of this though, so you can get a lot of power. The cost is that every time you take a shot, obviously, the disadvantage is that it's slow because all the power that you're accumulating needs to be accumulated over time. So you need to spend a lot of time like like putting the power into the elastic bands, right? Like doing the loading. Whereas the flywheel, once it shoots once, because it doesn't need to store, like it isn't reliant upon an energy storage mechanism, it can just shoot immediately after, or like just about immediately after, right? You can get much faster shots off with flywheel. So that's like one of the big things that you need to consider. As Alan showed, one of the ways that we worked around this in Turning Point, the fact that you needed, like, it was relatively more slow to use a catapult than, for example, a flywheel. The way that we got around this was by using double shot catapults, where you would shoot two at once. Because you have so much power, you're able to like easily fling two balls, like within the catapult arm, and with enough like energy to like turn the flags. And that was like one of the best ways to like to compensate for the fact that your reloading is your rate of fire is going to be much less than for example the flywheel. Let me think. The second advantage I would say about the catapult is that is when you consider the firing arc. So this is when it's compared to like a puncher, right? So a puncher, if you can imagine, it is what it sounds like. We'll get into punchers like in in later weeks. But if you can imagine, just like you bring similar to a catapult, it uses elastic bands and like stored energy, where you do work against the elastic bands to bring the puncher back, and then it also uses the slip gear where like instead of like flinging it in an arc, it like just the puncher just goes straight, hits the ball, and transfers all of its momentum or kinetic energy into the ball, and then the ball just shoots out straight at the target, right? One of the advantages we found when using a catapult was that because the catapult you like the puncher will shoot a ball straight at the target, right? Whereas the catapult shoots in an arc. In Turning Point, a common defensive strategy would be to try to like get in front of like the person that or the bot is that is shooting, and like block the shots. I know Alan's team like was like a master of this strategy, but because like with a well-built catapult, you're able to get around that slightly, because of the arc of fire, that the catapult's ball takes, making it much harder to like actually block the shot and letting you like do a lot of creative things with your shot angle.
Mm-hmm. Yep, that was a pretty general explanation, pretty good explanation of what catapult is and why teams gravitate towards it. Um, oh dear. Okay, I'll fix that in 2 seconds. But one thing that I wanted to, oh yikes, I was missing a constraint. Okay, one thing I want to talk about is, and Jeffrey has touched on this, is the slip gear. So
Slip gear.
yep, the slip gear is exactly what we have here. So if you look at it, you notice something strange about it. Like you see that, like one like, let's just say like a sector of this like gear is like it's completely like the teeth are shaven off, right? So there's like no teeth on the front segment. Whereas if you look at normal gear, there's teeth all around. So why do we choose this? It's like you'll see like very clearly after we're done the build, but basically like the gear like it'll mesh with another gear like when it's turning until it hits this like bald patch, like you can call it. And when it hits this bald patch, like the two gears are effectively not contacting each other anymore, which causes like the energy from the elastic bands to be transferred to like the catapult, resulting in a ball shot. So this is the option like teams gravitate towards when building like a catapult or puncher because of sheer simplicity. Because as you can see in this CAD that we're gonna do right now, like using a slip gear like greatly simplifies like this like mechanism, and unless you want to build something like a trebuchet or whatever, which is a lot more complicated, but this is like typically
Don't build
simpler,
trebuchets.
like less failure points is what teams want. So yeah, we'll show you how to like make a slip gear in CAD, by the way, at the end of the lesson, because it requires, and I'll just touch on how to make sketches as well because it'll be important when you guys start CADing. And it's actually not hard to make, so I'll just take like 2 minutes at the end to show you guys how to customize a gear to make a slip gear. But first we'll
Yeah,
finish the catapult.
for the shooting mechanism, like the consistency of the shooting mechanism, um, that just depends on your build quality. Like we found that so in my first year, like my build, well, I mean even today my build quality is not the highest, but like especially back in my first year, my build quality was like kind of it was like kind of duct tape and nails. Like I'll put it that way. You could see like the video I sent. That was that's an example of like that's a video of like the catapult I built in grade 10. It's not like the best quality, but that's just a good example. What we found with the shooting results is that it just basically really depends on how sturdy your build was, and if your build was really really sturdy. Okay, actually two things. One thing that you needed to I think that the consistency point is a really good point that you brought up in the chat, because one thing that you always had to keep in mind with your catapult is the elastic bands. Like even if your build was really really strong and like everything was like screwed in really tightly and didn't budge, the elastic bands, like if you didn't keep track of the elastic bands, they would actually like kill you a lot of the times. That's what we found, because what happens is that the elastic bands is what powers the catapult and like flings the arm forward to give it the shot. But then if you don't, but then the thing about elastic bands is after like that you stretch them and then like release them, stretch them and release them a bunch, they weaken, right? So if you're not always checking the elastic bands to make sure that like they're the right strength, then what will happen is that like during matches we were finding that like for some reason like we would like we would we'd be in a tournament, and then like 4 or 5 matches in we would start like finding that our catapult wasn't able to like turn the flags anymore, and that was because we forgot to like keep checking the elastic bands and like switch it out. So you need to be very mindful of the elastic band strength, and like have like a way to like consistently get the like the same amount of force being applied through your elastic bands. If you're able to do that, along with like solid build quality, like that's really really important for like anything that is experiencing a lot of stress, like the catapult arm. Then we found that the consistency was able to be there for sure. It's just that like you needed to always have that back in the back of your mind, right? Like to keep checking to keep checking every single match whether your bands were the correct strength. Does that answer your question? Another thing I'll show. Oh yeah, wait. So let me find the video. This is pretty cool.
Okay, wait. What I'm trying to do right now is to sync these gears up, because like right now, like if I rotate one, the other one doesn't rotate with it, because like these are on the same shaft. So I really want to fix this. Um, if you like go on to like the sidebar, like you can see like more detailed representations of each like part. You can like select like helper lines, like the planes for example, and like constrain these together, which is what I'm gonna do. I'm gonna constrain the XY plane with that, with the XY plane with this, and this is helpful sometimes, especially when your CADs get more complicated. Now you can see like the gears are synced up, and hopefully this works, and it does, yeah. So I just constrain like the two planes together, which you can find within origin. If you go like the part origin, and you can find the planes, which is really helpful sometimes. Yeah, that's this gear. Okay, we can move on to the top part.
Oh yeah, wait, Alan, your screen is black. I don't know why.
Is that screen okay?
Yeah, your screen said. Like alt tab and alt tab back in, I think.
Okay, I'll retry.
Another thing I was talking about with like catapult power is like in that YouTube video, like that's again from like it's in grade 9. You can see that it's so dumb. Like we were shooting from, it's like that's the entire field, right? And like we were shooting from like the furthest like corner, and we were still able to like shoot the ball and turn the flag. You could do that with a puncher and you could do that with a catapult, but like with a flywheel for sure. That's what I was talking about with like stored power versus like continuous usage of power. Where that like with a flywheel, there's just no way that you would be able to get the amount of energy you need to like shoot and hit the flag from like the opposite corner of the field.
I think it works. It should work now.
Yeah, we're good.
We're good? Okay, sweet. Alright, don't know what happened there, but let's move on. Okay, so we're gonna now power this catapult now, so we're gonna put a motor in. One note that I want to make sure you guys are wary of, and like Y Team had this issue as well. All the shafts we've been using are called low strength shafts, so you can notice that their diameter is pretty thin. But they're like, don't get me wrong, like these shafts are like really strong anyways. But like for like really high stress applications like a catapult, where you literally like you would put on like many bands to like
Yeah.
give it enough elastic energy to like give momentum to the balls. Like you want to use something called high strength shafts, and I'll just show you guys what a high strength shaft is. Where is it? Shafts. High strength shafts. So they're basically normal shafts, but much thicker, like much thicker.
Yeah. You're able to use low strength. I found if you close the distance as much as you can between the two, like between like the two like points where the shaft is being held. If you like reduce like if you make that distance as small as you can, like one C channel length plus like like about like less than if you get that to like an inch or something like that, then low strength like could work. But yeah, high strength for sure is like a good usage here.
The main issue with high strength is cutting it down to size and then
Drilling.
making sure that you file it so it doesn't scuff up other things.
The main issue with high strength shafts is that you can't put high strength shafts through normal holes.
Yeah, you just drill that out and like you can get it you can get it roughly frictionless. When you put in the bearing, it's almost I found that like you can get it to be almost as frictionless as a regular bearing. It's not like I don't think that that's the issue.
Oh yeah, I mean, okay, well, yeah, okay. If you have like competent drillers, like for us, like we drilled, like we were planning, well, we weren't planning to switch to high strength shaft, but like a couple people on our team like decided to go high strength shaft the day before provincials, in grade 10, and then they drilled into the wrong hole. So like on the entire like so like basically like like you can't like do anything like or if you drill into the wrong hole like you just lose, right? So the entire bus there, I was trying to like figure out a way to like fix so moral of the story is like don't drill last minute, and like when you're drilling make sure that you're drilling the right hole, because if you're not drilling the right hole then it's really hard to like fix it.
Yeah, moral of the story is you don't want to be building like before a competition. Like
don't be doing major rebuilds before
like, well before a competition, or else like you might have issues. Like for us, like
you're gonna have a lot of issues.
For us, like we did like last year, like a big mistake like my team made. Like we rebuilt like 2 weeks before provincials. Like we respected the fact like you should have your build done like well before like a competition. So like we got it all working like 1 week before, and like we had 1 whole week of testing, and it had like 0 issues. But on the day of provincials, a lot of things just decided to go wrong for no reason that I'm still confused today. So just like a general note, you want to make sure your robot has been proven to work like for like let's just say at least a month or something to be safe.
Like there's nothing better than like the best like the how do you say it, like so cutting things out is like good, right? Like so cutting things out is good, building them out is even better, and then like testing them on like let's say like a field at your house is even better than that. But there's like literally no replacement for a tournament experience for like what happens when like we get rammed by somebody actually trying like who's not like going easy on us because like like we're on the same team, but who's actually like trying to like beat us and win the game, right? Like trying to subdue a robot. There's no replacement for that. So like you definitely want to make sure that like whatever robot you're working with has like has gone through the tournament cycle.
Oh, just a note, like you can see like inside it's a green cartridge, but in real life I'll probably
use
a red cartridge because red cartridge is 100 RPM, so it favors torque over speed, which in high torque applications we probably want torque. So I'll probably use like red, but based on like testing, like for example how heavy the game objects are, or like how far do you have to shoot the objects or whatever, this can like vary wildly. If I just need a weak catapult, I'll just probably run 200, maybe like make the gear ratio like a bigger gear ratio, like a bigger gear to or like a bigger smaller gear to a smaller bigger gear. I know that totally sounds confusing, but yeah.
Another thing that's like more advanced, what you could do with a catapult is you could build what are called ratchets. So like for a catapult, when you bring the arm down, when you have the arm down, right? Normally what happens is that you need to like continuously be running the motors in order to keep the arm at the loaded position. Does that makes sense? Because the elastic bands are obviously work like exerting a force to like bring the arm back up. So in order to like have it in the loaded position, you need to be exerting a constant force. This is a more advanced topic, but like if you have if the interest to like go like look into it, so that's like not the best thing on your motors to generally it's like not advised to be like running your motors at like a reasonably high like at like a high power, like especially if it's like being run like constantly like throughout like because basically when you load the catapult like you're literally gonna be running the motor like the entire time when it's loaded, which is like can be cause really big problems for your motors. So what a ratchet is a ratchet is like how do you like a ratchet basically makes it so that it's easier to go like to spin one like it prevents the system from spinning in like one direction at the but it makes it like slightly harder to spin in like the correct direction, if that makes sense, but it makes it impossible to spin in the other direction by like jamming it from spinning in the other direction. So the advantage of this is that even though you would have to exert like a slightly more force to like load it to like bring the catapult arm down because of the friction on the ratchet, what it will allow you to do is like once it is in loaded position, then you could just turn off your motors and like the ratchet jamming will like hold the arm in the loaded position until you like decide to shoot it, because your catapult is only going to be so your catapult motor is only going to be rotating ever in like one direction, right? You're never going to be rotating the other direction. So like that's one benefit of using a ratchet in this application. Like I think ratchet is actually really if you're building a catapult, I think that you should always be considering to build to build a ratchet mechanism.
I don't think many teams actually did it, but I hear ratchet noises in 21S's reveal. Oh yeah, like, generally like a lot of strain being placed on the motor is bad because if the motor's like in like during stall torque, like the motor's not moving, like all the electrical energy you can say is being converted into heat, which is definitely not good. So if you have a ratchet to hold it in place, like Jeffrey said, it'll be a lot nicer. And a ratchet, by the way, is just like if you guys play badminton or volleyball, it's basically like those cranky things that you use to set up the net. Like basically allows you to crank one way and it doesn't let you crank the other way because or else like the string will lose its tension. All right, this is looking pretty interesting. All right, we're almost done. Just gonna touch this up a little bit. Oh, by the way, I just want to talk about two things that I kind of did. So, one, notice that we used two sets of gears, right? Like you can like you can argue totally you can just use like one set of gears. Why did I add like a second pair? Like just because like catapults are such a high stress mechanism, you want to make sure the load's distributed over like two sets of gears. Like because if you put a gear under too much force, like it will actually crack and snap and do bad things. So you want to make sure you distribute the load. Also, notice here, I put two C channels into like a box shape, and this is something called boxing or boxing C channels, and it just makes this a lot stronger because, again, catapult high stress mechanism, you want to put a lot more bracing on it. So yeah, it's a lot less prone to like bending and like shear forces or not shear forces, but a lot less prone to like bending or whatever or deformation if you put two together. Okay, let me build the paddle. Oh wait, whoops, wrong library. Okay, and now like the final thing we need to build is a hard stop, which is basically to make sure the catapult doesn't like swing too far. So it only swings like it only crosses like a certain like distance and doesn't like swing way too far. I'll just put two standoffs in real quick. This is just to like stop the balls from like moving too far back. But again, depending on your application, like this might differ. Okay, let's say we want to go this high. So we're just gonna build something to stop this paddle from going too far down. I'm just gonna do a simple and crude solution for now. How many holes is this? 1, 2, 3, 4, 5, 6. Okay, let's grab a 6x2. Structure C channels. And we're just gonna use washers to make sure it clears the gear teeth a bit better. And after this, I'll just show how this will be rubber banded, and then the slip gear. We have time to cover slip gear, and then we can call it a day here. So let me just put this on, and it should go on about here. So yeah, so basically hard stop. If this paddle moves down far enough and it'll hit this, it'll stop the catapult. In reality, you probably want to box this as well to make sure like the top flange doesn't really bend down. Actually, I'll do this right now because it's important. Because like due to high stress, if the top flange bends down, you're gonna get inconsistent shooting because the catapult will stop at different angles every time. So I'm just gonna box this to make sure it's nice and strong. Okay, and yeah, we're pretty much done. And for banding, there's two options. One, because you want the catapult to, I'm just gonna bring the catapult down. Hold on. Inventor's being slow. Okay, I'm just gonna bring the catapult all the way down. What is it doing? Okay, so if we bring it all the way down, we want it to spring like this way, right? So we can either like band this point, like band this part down to here so it shoots upwards, or you can like band it somewhere at this point and then like band it across like this. Just like band it any configuration such that the catapult will want to move like this. That's a bit too far. It'll want to move like, okay, dragging things in Inventor is kind of weird. I'll try to do it. Really annoying sometimes. Make it want to move like this. And then up to the point it hits the hard stop, it'll stop. You know what? I'm just gonna use an angle constraint. This is too painful. Okay, angle constraint here. And you want the angle to be, let's just say like, try 15 degrees. Nope. And yeah, this will be like its shooting position, and it'll stop at around 140 degrees, and this will be its fully up position. And yeah, so that's basically the catapult. And now slip gear time. So okay, this is basically catapult, and now we're just gonna go back to the slip gear we mentioned earlier. To make one of these is pretty simple, but you're gonna have to learn how to make sketches. So let's just do one for fun. So let's open up. Let's go get a gear. Where are the gears that are in motion? Gears. Let's just take a 62th gear. Okay, and now if you double click it, you can basically edit it as a part. And then you can do a 2D sketch on it. So we're going to do that, and we want to do it on this surface. This technique, by the way, if you want to cut parts, like in Inventor, it's like the same idea. So we're just going to want to, I wonder, hold on. Yeah, okay, so let's just say we want to cut like a certain amount of teeth off. So just going to put a point here where we want to start, and put a point like, say here where we want to end. And then we're going to use the arc tool, 3-point arc, to make an arc. Like this. Okay, and then we want to, this part can be sloppy, so like you just have to make sure it encapsulates the area of the teeth that you want to cut off. So I'm just going to put 2 random lines like this, and I'm going to make another arc. Like that. And you can see like this this area encapsulate the teeth that we want to shave off. And now we're basically done. So we can just click extrude, and we click the area we want to extrude, and then you make it go the other way and make it cut. And if you click OK, you notice that the teeth are now cut off. And I'm going to undo that because I actually don't want to do this to this gear. So yeah, this is basically all we wanted to cover for this week. So do we have any questions? Alright, see you at round 1. Okay, it looks like we don't have any more questions, so we'll just call it here. Thank you all for coming, and we'll see you guys next week. Have a good day.